Hi, everybody, and thank you for joining us today for our webinar, Insulation Systems for Liquefied Natural Gas Piping. My name is Kim Melton, and I'm going to be the moderator for today's presentation. Before we get started, I do want to go over a few logistics. First and foremost, we are working from home. So if we run into any technical difficulties today, we're going to pause the presentation. We'll spend about 5 minutes attempting to fix it. If we can't fix it in that time frame, we're going to cancel today's presentation, and we will record it and send you a recording that you can watch at your leisure. This will be available for you on demand to watch however you see fit, or even share it with your colleagues. So hopefully we won't run into any technical problems, but if we do, that's our plan of attack. We'll also be answering questions live at the end of the webinar. You can submit your questions via the Q&A feature, and you should see that to the right side of your screen. Now, if you don't see Q&A on the right side of your screen, if you hover your mouse over the center of your screen, you'll actually see a series of circular icons pop up across the bottom. The second one from the right is a question mark in a square, and if you click that, it'll open a dialog box to the right of your screen that will allow you to submit any questions you may have, and we'll address those at the end of the presentation. Also, the information provided in the webinar today should not be used as a substitute for professional engineering design and/or documentation that's required by building codes, contracts, or applicable laws. And you should also refer to our specific application guidelines or instructions and guarantee requirements on all projects. Also, we'll be concluding the webinar today with a survey, and this is your opportunity to provide us with feedback on how we do. You can ask any additional questions you might have about the topic of the webinar, or even suggest topics for future webinars. And this survey is really part of how we deliver the JAM experience to you. Now, you'll see those four values in the bottom left corner, and that's people, passion, perform, and protect. And those are the four values the JAM culture is based on. And we believe really it's critical to make sure that we hear and understand and respond to your needs in order to deliver the JAM experience to you and have the best interaction with you. So we offer webinars like this one to help educate the market and be a tool and a resource for you and your business. But this isn't just a one-way street. So your feedback is a key component to helping us better evolve to meet your needs. So if you have any suggestions as to how we can do that better, or maybe you feel like we've missed the mark today, we encourage you to fill out the survey, and we'll use your feedback to improve our webinars and provide the information that has the most value to you in the future. Now, we're also asked whether or not we send out these webinars upon their conclusion. And while we don't actually send out the webinar deck itself, we will post a recording of it online. You can access that on demand anytime, totally free of charge. You can share it with your colleagues. And this really ensures that you can have the presentation as it is today within its full context with all of the content that our presenters are going to share with you surrounding the topic. So with that, we're going to go ahead and get to some introductions. Joining me today are Jack Bittner and Jim Young, and I'm going to kick it over to Jim to introduce himself.
Hello and welcome. My name is Jim Young. I'm the Cold Insulation Specialist Engineer for Johns Manville. I've been in the mechanical insulation industry for 22 years, and during all of this time, my focus has been on cold insulation applications, working for Dow Chemical, ITW Insulation Systems, and now Johns Manville. I have done a lot of work to help design and update corporate and project specs for numerous LNG projects around the world.
And I'm Jack Bittner. I'm the Senior Industrial Insulation Product Manager at Johns Manville. I've been with JM 16 years, but in the industrial insulation industry for a little over 40 years now, which is difficult to say, but that's how long it's been. Mostly I've been on the hot side. I am learning very quickly the cold side. Today we're going to talk about LNG pipe systems specifically. We're going to talk about the design criteria for the insulation system, the system design, materials, and then a little bit on installation and maintenance. But there's a lot there on installation and maintenance, and I expect we'll be in the future having other webinars as well that may get more in detail on those, but we'll touch on them a little bit at the end. LNG pipe systems are extremely unique. The things that make them unique as they are, the biggest one is the temperature range. Minus 265 F or 165 C is extremely cold. And most often this equipment in these units are located in high humid environments, high temperature environments. They're usually along the coast where there's not only the temperature, the humidity, there's salt sprays, there's all kinds of things that make the installations difficult. And you combine the hot and humid with the low temperatures we're dealing, and you've got a huge vapor drive and serious temperatures to consider. So that's probably the two biggest things that make these LNG systems unique. In addition, the pipe diameters quite often get up to 48 inches in diameter, big, and the length. Some of these pipelines on the coast from the ships are in excess of 1,000 feet. And when somebody designs a system like this, you're looking to see it last 15 to 20 years easily. So all these things make this LNG pipe insulation systems extremely unique, more so than on the hot side because of the vapor drive. And we look at it, the engineered system, as a puzzle. You've got the design criteria, the system design, materials, installation, all of which we're going to talk about today. And if one piece of this puzzle is missing or not done well, things don't match up and you're looking for trouble. And I'm trying to turn it over to you, Jim. I think you have it.
I do. Thank you, Jack. This is Jim Young. I'll be presenting the portions of this webinar on design criteria, system design, and materials. The first of the key aspects that we'll discuss today are the design criteria. The design criteria are the issues that must be considered when performing the insulation system design. The first of these seems trivial, but is actually probably the most important. Why are the cryogenic LNG pipes being insulated? Seems like an almost trivial question. There are many possible reasons, but the two most often considered critical in LNG applications are shown in blue at the top of the screen here. Condensation control, and then process control to limit the heat gain to reduce boil-off gas. By designing an insulation system to accomplish these two goals, all of the other reasons to insulate that are shown here will also be largely accomplished. There are many other design criteria that must be considered, including specifications, code compliance, desired service life, ambient and the physical environment, operating conditions, and the inspection and maintenance plan. However, the most important design criteria that must be considered is where the facility owner or specifier wants to operate on what I like to call the cost-performance continuum. An insulation system with higher performance has more redundancy, better materials, and better system design built into it. This redundancy and better materials help to prevent problems, and if a problem does occur, it buys an owner time to find the problem prior to irreparable system damage. This damage is most often caused by water or water vapor entrance into the insulation system, which causes loss of insulating ability, ice formation, physical damage to the insulation system, and other problems. Higher performance costs more upfront, but in LNG pipe insulation applications is usually justified through lower life cycle costs achieved primarily by yielding a longer lasting insulation system. While the decision on where to operate in this cost performance continuum is up to the specifier or facility owner, JM recommends higher performance LNG pipe insulation system design, and this is usually what is done for LNG facilities. All right, the second of the key aspects that we will discuss today is the insulation system design. Based on the design criteria, which we just discussed, the specifying engineer must perform the insulation system design. This will include a number of important aspects, the first of which is material selection. This is not just selection of the insulation to be used, but all of the various components of the insulation system as shown here. Today, when we discuss materials, we will only have time to focus on the main three, which are shown in blue: insulation, vapor retarders, and jacketing. We'll mention some of the other materials briefly, but our focus will be on these three. The other material categories are important, and JM would be happy to discuss them with you offline, but we won't get into the details on them today, just from a time constraint point of view. Another key design decision is the total insulation thickness and the number of layers required. The total thickness is driven by the design criteria chosen, which are usually, as I said, condensation control and heat gain limits, but also by the insulation material used. As we will see later, there's a wide range of thermal conductivity and hence insulating ability among the insulation materials commonly used on LNG pipe. The number of layers used will be either 2 or 3 for the 2 most commonly used in LNG insulation materials, PIR, that's polyisocyanurate, and cellular glass. Whether it is 2 or 3 layers depends on the total insulation thickness required. For a total thickness less than around 5 to 6 inches, a double layer system would be used. At a total thickness above this, a triple layer insulation system would typically be used. And again, that's for cellular glass and PIR. The next key design decision is how the insulation joints will be staggered. This applies to both the circumferential or butt joints as well as the longitudinal joints. JM recommends that all joints between layers be staggered. In the top 2 pictures, you can see the recommended method for staggering the butt joints. Requiring the butt joints to be staggered in this manner between layers improves the integrity of the insulation system and impedes water and water vapor entry through these joints by forcing any water entering the insulation system to take a more tortuous path through these staggered joints. The bottom picture shows the recommended staggering design for the longitudinal joints. The longitudinal joints in each layer should be staggered by about 90 degrees from the joints in the adjacent layers. As with the butt joints, staggering the longitudinal joints in this manner makes a more tortuous path for water entry. In addition, the joints in the outermost layer should be located about the 3 o'clock and 9 o'clock positions on the pipe. Forces exerted on the pipe are most likely to occur at the top and bottom, the 3 and 9 o'clock positions, the 12 and 6 o'clock positions. So it's best to locate the joints at places where these forces will not be exerted, which would be at the 3 and 9 o'clock positions in the outer layer. Here are some pictures of joint staggering. The left picture shows the butt joint staggering at an elbow location. The right-hand picture is a little harder to see, but it shows the inner layer longitudinal joints at the 6 and 12 o'clock positions, with the neighboring insulation pieces having its outer layer longitudinal joints staggered by not quite 90 degrees, but more than sufficiently. Here's a drawing and a picture of the staggering of both butt and longitudinal joints when curved segments are used. On very large diameter pipe, you can't use insulation half shells, so you use curved segments, as is shown here. In both pictures, you can see the staggering of the longitudinal joints by about 50% the circumference of the curved segment. In the right-hand picture, you can see that the inner and outer layer also have their butt joints staggered. Another key design aspect is the design of the insulation joints and the requirement for how and where joint sealant is applied. Flat insulation joints have historically been the most commonly used type, and the pictures on this slide show this joint design. However, there are alternatives such as shiplap and tongue and groove that can be used. In our experience, properly installed flat joints are usually sufficient. The pictures here show this joint design. The spec should require that joint sealant be applied as a thin, even layer across the entire joint face. The thinness of the joint sealant minimizes the ability of the joint sealant to act as a thermal short and transfer large amounts of heat through it. You want to avoid that. The even application across the entire joint face maximizes both joint strength and joint resistance to water or water vapor movement through the joint. Lastly, joint sealant is typically not used on the innermost layer with PIR insulation, but required on all joints in the second and third layers. This allows the innermost layer, which sees the greatest temperature change from installation to operating temperature, best accommodate any expansion or contraction that occurs. In the left picture, you can see that there is no joint sealant being applied to the innermost layer, while the right picture shows the use of joint sealant on the second layer. Where joint sealant is used, it should be applied, as I said, as a thin layer across the entire joint face. That's a key design attribute. The next key design aspect we will discuss is contraction joints. There are many designs for and opinions about where contraction joints should be used. They are most commonly used in the second and third layers for PIR insulation systems. JM can assist with design and spacing of these. There are calculations that can be used, and JM can help you with those to determine the spacing. They are usually constructed by filling a small annular gap between adjacent insulation pieces with mineral fiber insulation and then compressing this fiber. If this gap opens up due to contraction, the mineral fiber will expand to fill the gap. Expansion joints in adjacent layers should be staggered from each other, again to provide a more tortuous path for water or water vapor to pass through them. The next key design aspect is pipe supports. Insulation must be used at pipe supports, and this can take many forms. On rare cases, super strong resin-impregnated wood is used, but this has very poor insulating ability. More commonly, high-density polyurethane is used at the supports, and this can range in density from, say, 10 to 20 pounds per cubic foot, with a higher density having much higher compressive strength, but also having comparatively poor insulating ability versus the neighboring PIR insulation, or cellular glass insulation. High-density versions of Trimer PIR from JM, they don't get as high as 10 or 20 pounds per cubic foot, but they can work in some support applications. This would be PIR in the range of 4 to 6 pounds per cubic foot. Using this can often yield acceptable strength at the supports without sacrificing insulating ability. JM can offer help with selection of PIR necessary at pipe support locations by helping you to perform the right calculations to verify that the strength of the insulation would be sufficient at the support location. Another key design aspect is selection and design of the vapor retarder system. This is of vital importance to the performance and longevity of the LNG insulation system. We will discuss the vapor retarder material choices later. The system designer must decide how many vapor retarders to use and where they are to be located. Typically, a primary vapor retarder is used on the outside of the outermost insulation layer, and a secondary vapor retarder is used under the outermost layer of insulation. The system designer must also determine how the vapor retarders will be closed or sealed and how they will be held in place. The vapor retarder used on elbows and fittings may differ from that used on the straight pipe. For example, a mastic fabric mastic primary vapor retarder system might be used on the non-straight pipe, that is elbows. The picture here shows the secondary vapor retarder applied and the joint sealed. It also shows the third layer of PIR insulation being applied. Over this third layer, the primary vapor retarder will be installed, and then the protective metal jacketing. The next key aspect is the design and location of vapor stops. The key purpose of a vapor stop is to isolate any damage caused by water penetration into the insulation system. Vapor stops are typically required at specific places on LNG piping, such as on either side of valves or flanges. In addition, they are also recommended to be located periodically on long runs of pipe. The frequency of their use depends on where the specifier wants to operate on the aforementioned cost-performance continuum. In the left picture, you can see a vapor stop applied to a triple-layer staggered butt joint on either side of a flange. In the right drawing, you can see the details of one design for a vapor stop. We will not be discussing the details of vapor stop design today, but the key is that the vapor stop seals the end of the insulation and connects the pipe to the primary vapor retarder with a low permeance barrier to longitudinal passage of water or water vapor. The next key aspect is the design of the metal jacketing. We'll discuss metal jacket material selection later. The metal jacket joints should be oriented to naturally shed water or face away from the prevailing winds. There are many other aspects of LNG pipe insulation system design that we do not have time to discuss today, but JM can definitely help with many of these. Now let's turn our attention to the materials used in LNG pipe insulation systems and selection of these materials. As mentioned previously, there are many different materials used in LNG pipe insulation systems, but we will talk today of mainly about the three shown here in blue: insulation, vapor retarders, and jacketing. So let's start by discussing the insulation materials. The main purpose of insulation is to reduce heat flow through it, but it also helps to reduce water entry into the insulation system. Insulation performance depends on many factors, and there is no perfect insulation material that excels at all factors. Some of the factors that are important when choosing an insulation material are density, thermal conductivity, commonly called K factor in North America, or lambda outside of North America, chemical and water resistance, cost, availability, and the thickness requirements. The selection of an insulation material should be based on the relative importance of each of these factors to your specific situation. Consider your design criteria and where you want to operate on the cost-performance continuum when making this choice. Far and away, the two most commonly used insulation materials in LNG pipe applications are polyisocyanuric, abbreviated usually PIR, and because that is quite a mouthful, like I said, we have the short acronym. Johns Manville makes a premier grade of PIR for use in LNG applications called Trimer 2500. The other material that's commonly used is cellular glass. Globally, the use of cellular glass on LNG pipes is small compared to the much more often used PIR. Both PIR and cell glass are closed cell. The density of PIR is roughly 1/3 that of cellular glass, so insulation systems based on PIR weigh a lot less than cell glass systems. PIR is easy to fabricate both in the shop and in the field and is comparatively quick and easy to install. Cellular glass is harder to fabricate for several reasons. It's made of glass, which requires special tools, and it comes in smaller pieces. PIR is significantly lower in cost per board foot, which is the pricing unit. That is, a board foot is the pricing unit typically used by the manufacturers. The better lower thermal conductivity of PIR leads to a lower insulation thickness being required compared to cellular glass. This in turn leads to less material being required for PIR, which yields lower material costs. The graph on this slide shows an example of the thickness of PIR and cell glass needed for a typical LNG scenario at various levels of relative humidity. Of course, as the relative humidity increases, the thickness required for both materials increases, and this increase begins at about 87 to 88% relative humidity, as you can see in the graph. Below that relative humidity level, the design criteria of limiting the heat gain dominates. But at all levels of relative humidity, the thickness required for cellular glass is 1.5 to 2 inches greater than that of PIR. Converting this thickness into an amount of material required, the cell glass would require about 28% more material than would an insulation system based on PIR. Let's consider how the K factors, or lambda, that is the thermal conductivity, of several LNG insulation materials translate into the total thickness required and the number of layers required. As mentioned on the previous slide, the superior, that is lower, thermal conductivity of PIR compared to cell glass translates directly into a lower thickness being used, but this thickness reduction is only part of the story. Using PIR insulation also yields an overall outer insulation circumference that is 10 to 20% smaller than that of cell glass. This smaller outer circumference means less material is used for joint sealants, vapor retarders, metal jacketing, etc. Now let's take a look at the total insulation thickness and number of insulation layers required for PIR, cellular glass, and let's include a relative newcomer to the LNG pipe insulation party, silica aerogel. For the reasonable climatic scenario described in the table, you can see the insulation thicknesses required for each material. The greatest thickness required is for cellular glass, while the very low K factor of aerogel yields the lowest thickness. However, total thickness is not the whole story. Look at the last column, which shows the number of layers that must be installed for each material. For the PIR and cell glass, there are 3 layers needed. However, even though the total thickness required for the aerogel is the smallest, the number of layers that have to be each individually installed is 12, 4 times the number of layers for PIR and cell glass. The reason for this is that the aerogel comes in a maximum layer thickness of only 10 millimeters, which is less than ½ an inch. Compared head-to-head, PIR is more economical insulation solution for LNG pipe than is cellular glass. PIR is less costly material, and because cell glass comes in shorter sections than PIR, you have to install 50% more pieces of cell glass in a given run of pipe. This increase in number of pieces means there are more joints that have to be sealed, which means greater labor costs to install and more joints to potentially leak. The better lower K factor of PIR drives a lot of beneficial cost factors. PIR is used at a thinner total thickness, uses fewer layers than aerogel, is the least costly LNG insulation material used, and requires less of the expensive accessories compared to cell glass, like vapor retarders, jacketing, and sealants. The thinner total thickness of PIR compared to cell glass can also be a benefit for space savings at the LNG facility. Insulation system cost and performance is, of course, only part of what has to be considered when selecting material. The long-term performance is also of great importance. The performance of PIR insulation in LNG applications is outstanding. I like to say nothing succeeds like success, and we have a lot of history and a lot of success. PIR in general, and Trimer PIR specifically, has been used in the majority of the world's LNG facilities, where it has demonstrated 20 to 30 plus years of service life. This has occurred in all parts of the world, including the USA and Canada. So, to kind of conclude this area, PIR insulation on LNG pipes works well and has worked well in hundreds of the North American and global facilities for many, many decades. Now let's turn our attention to the next material, which we will discuss, which is the vapor retarders. Selection of vapor retarder must be based on its permeance, which simplistically is the rate at which water vapor passes through the vapor retarder. Since the main purpose of a vapor retarder is to severely limit water vapor movement toward the pipe, the permeance of the vapor retarder system is its most important property. Permeance is measured in units of perms, and a lower value or a lower perm rating is better. The typical requirement for the vapor retarders on an LNG pipe insulation system is a permeance of less than or equal to 0.01 perms. However, watch out for ideal lab performance compared to actual real-world field performance. There are vapor retarder materials which might have a lab result of 0.01 perms with no joints present and in pristine lab condition, and in the carefully controlled flat test geometry, but which would not work well in an actual LNG application due to the rugged environment and the presence of so many joints. Besides its permeance, there are other important attributes to a vapor retarder. These include puncture, abrasion, and tear resistance, flame and smoke performance, tensile strength, and of course, cost. In general, there are some specific materials that are recommended for use as vapor retarders in LNG pipe insulation applications. For the primary vapor retarder, the three most commonly used and recommended materials are rubberized membranes, which are expensive but are the most commonly used materials, low permeance plastic films like our Ceranex 560CX, but there are other types of plastic films as well, and mastic fabric mastic, which is a very labor-intensive material and relies very heavily on the skill of the installer to achieve the desired performance, really to achieve the desired thickness, because without the proper thickness, mastic fabric mastic will not yield the correct performance. And thickness is solely dependent upon the application. For the secondary vapor retarder, there are two materials typically used: low permeance plastic films like the Ceranex 560CX from Johns Manville, and mylar aluminum mylar, or MAM type films, or polyester aluminum polyester. Those mean the same thing. To close my portion of the presentation, I want to remind the audience of where the vapor retarders and the joint sealants are used in a typical PIR insulation system in an LNG application, because these are sometimes confusing. We talked about them before, but this is just to reiterate. These locations are shown on this slide. In a two-layer insulation system, joint sealant is used only on the outer layer, and there are two vapor retarders, primary and secondary, located as shown. In a three-layer insulation system, joint sealant is used on the second and third layers, but not on the first layer. There are still two vapor retarders used, primary and secondary, located as shown. Now I'll turn the presentation over to Jack, who will address the jacketing materials, installation, and maintenance portions of the webinar. It's been a pleasure. Thank you.
Thanks, Jim. So jacketing, the primary purpose of the jacketing systems for all installations, but particularly the low temperatures we see in LNG, is it protects the system, and especially the vapor retarder, from damage from physical abuse, punctures, and even the UV rays from sunlight. The jacketing most often used is aluminum and stainless steel, and in many applications there's more stainless steel jacketing than aluminum, because in a lot of the areas where you see the LNG installations, they're in very corrosive environments, and there are also areas with high flammability concern. In addition, Jim talked about the thickness of the insulation that about a relative humidity of 88% and above causes the thickness to significantly increase. One way, if you're running out of room to cut down on the thickness of the insulation, is consider using painted aluminum like a white to help control condensation in those applications. And in all cases, the metal jacketing should have a 3-layer, 3 mil thick, factory laminated polyfilm moisture barrier on the interior surface. This helps prevent the corrosion on the interior surface of the metal jacketing, which will manifest itself in pitting, and pitting becomes a hole. And you don't want holes in any of the jacket systems in LNG applications. There's also a variety of attachment devices for metal jacketing. Mainly the purpose is to hold it in place. For the LNG applications and the temperatures we're dealing with here, bands only are what's required. There should be no rivets, no screws, no staples, no anything that might damage the vapor retarder. One thing we're asked about fairly often is jacket joint sealant, and this is caulking to eliminate of the jacketing system to eliminate water entry through the jacketing joints, circumferential and longitudinal. We don't have any test data or science on this, but it does seem to make sense. One caution, though, is it may also limit water evaporation from the inside of the insulation system out. But in the LNG applications, it might be a sensible thing to do. Again, we just don't have any data on it. But if it is specified, the sealant should be applied on the inside joints of the jacket, longitudinal and circumferential joints, and not as a bead on the outer joint lip. Now let's talk about installation, which I think, in my mind, is one of the most critical parts of this puzzle of LNG engineered system. At the temperatures we're talking about here, anything that's not installed properly is not going to last anywhere near its anticipated life cycle. You can take the best design, the best material, and have an improper installation, and the system will fail. So what are the requirements of a successful installation? The first thing is the selection of the contractor. The contractor must be familiar with the materials and the temperature ranges that we're talking about in LNG applications. It's just, I can't stress how unique it is, and the skill level you need with your contractors. One of the key issues is the proper application of the joint sealant. As Jim mentioned, it must be on both surfaces, thin layers, and definitely not on the inner layer, but thin layer of the joint sealant on the both joints that are going to be touching each other on the insulation materials. And the continuity of the vapor retarder. It must be installed without pinholes, without punctures, and it must be tight so it can function as the vapor retarder. And vapor stops are key as well. Jim mentioned the vapor stop application must go from the pipe all the way to the primary vapor retarder and be completely sealed. And expansion and contraction joints must be designed into the system. We have recommendations, but the frequency of them depends on the installation, and the engineers usually specify that. Outdoor, everything is pretty much outdoor in LNG. And they're also on the coast, generally high humidity areas, where overnight The dew is going to be on everything by the time you show up in the morning. In addition, in the coastal applications, there's a lot of rain that occurs any time of the day or night. So we recommend the installation to be in completable sections for that day. Only insulate what you can cover with a vapor retarder completely that day. If you can't finish it that day, you're going to have to cover it with tarp or visqueen or some other plastic sheet, but ideally it must be done that day just due to the climates that we operate in. At Johns Manville, we do have several means for you to get installation and design support. These items are on our website, one of which we're showing here, which is the installation guide for LNG systems for Trimer. But call us for any help you need or visit our website. And finally, maintenance. Maintenance is the next critical part. Once it's designed, once it's installed properly, now you've got to maintain it. If you want it to last 20 to 30 years, you can't just put it on and ignore it. The insulation system is an asset that you really want to take care of. And we're sometimes asked, how often should I inspect the system? Well, it depends on many factors. Ambient condition is the key thing to consider. Some of these installation locations have very harsh environments, very high humidities, very hot temperatures. On the coast where there's ocean spray and possibility for corrosion. So those kinds of systems will certainly require more often inspection than not. In addition, the system complexity. Installation in cryogenic applications for insulation and the vapor barriers and vapor stops and everything associated with it is an extremely complex system. And just due to that complexity, you'll want to inspect your system more often than not. Because as the systems age, you may have problems with the jacketing coming loose, or you certainly want to look for any water or moisture problems, and particularly ice. If you've got ice, you're in trouble. All these systems are important, and the designed system quality will have some impact on how often you should inspect your system. You remember the cost performance continuum that Jim discussed earlier. A higher performing and higher cost system up front will also need less inspection and less maintenance down the road. So what do you really look for? Well, the primary thing is any moisture, particularly ice, at any low spots in the system or on the pipes. And a low spot might be the middle of the pipe between two support shoes, or on a vertical application at the support rings, or certainly at the bottom. You also want to look for any holes or breaches in the jacketing or in the vapor retarder. If there's a hole in the jacketing, odds are you're probably going to have a hole in the vapor retarder too. You want to fix these immediately. Loose banding, loose or jacketing, obviously there will be reducing the protection function of the jacket for the vapor retarder. And caulking failure, especially at flanges and valves or any other joints. Any caulk is not permanent. And to expect multiple years out of a caulk joint, I think whether it's a hot or a cold system is pushing your luck. Then we've got the issue of minor problems versus major problems. If you're going to have a problem, you want it to be minor. If you catch it early, correcting it's a lot easier, less expensive, and maybe you don't even have downtime to correct it. And what is it? A minor problem? Well, look for evidence of ice or water filtration into the system. If it is minor and you catch it early and you're watching out for it, you can fix it immediately without having to shut down the entire process. Major shutdowns are going to be required if you have any ice or water in the system already. That's going to require removing the insulation, inspecting the pipe for any damage, and then rebuilding it completely to ensure the vapor retarder continuity. And that kind of repair will require a downtime. So to conclude, pipe insulation in LNG must be engineered. It's a unique system, and you really need to treat it as such. The repairs are going to be extremely costly and very difficult. As I just mentioned, it requires a shutdown of the system. Experienced installers for both the initial installation and all the maintenance are required. I think the installer is the key to everything here. So you've got to carefully select them. There are also significant acoustic challenges in LNG systems, which will be included in a subject in another webinar we will be having upcoming here shortly. But again, executing on the 5 key aspects will help ensure your systems operate as it's engineered for as long as you engineered it for, if you keep up with the maintenance, 20 years, 30 years.
All right, thank you, Jack and Jim, for that presentation. Jack, if you want to pass the ball back to me, I'll go ahead and take us through some additional resources.
Just trying to
We're
do
good.
it.
I'm all
you
set.
should have it.
Set.
Okay.
I got it. Thank you. So we do have some additional resources for anybody who is looking for more information about LNG or even high temperature stuff. So I'm going to walk us through that really quickly, and then we'll get to our questions. We have had a lot of questions submitted, so we will answer questions up to the half hour after the webinar concludes. So in Rocky Mountain time, that's 1:30. Where you are, will be on the half hour of wherever the time is that you're located. So we will have that all recorded. Any questions we don't get to today, we will answer your questions privately. We'll send you an email, and so they will be addressed. If not in the presentation today, you will get an email from a JM representative. So with that, I'm going to talk about some resources we have. So we do have some online resources. Coming soon, we will have an LNG and cryogenic digital resource page. This will have information on the products that we have available for these applications. This webinar will be hosted on that page. We'll also have installation guides, just a variety of resources for anybody who's looking for more information about installation systems for cryogenic applications. We also have the source. It's our installation intel, the source, and it is this is an online digital library where we host a lot of technical and educational information. So all of our recorded webinars live here on the source. You can also access ebooks, our blog. We have technical documentation, a list of our products, and then tools available to you. So this could be, we have a smart binder tool that you can download on your phone to get access to all of our data sheets and our technical documentation, like safety data sheets. You can have that right there on your phone, quick and easy access. We also have the part tool, which will help you for high temperature applications, which will help you weigh which material would be ideal for your application. So if you would like to access the source, you can do that from the industrial page on the Johns Manville website. There's a button to the right side of the screen that says the source. You can also click on our webinars on demand, and that will take you to the source, landing on the webinars page. Also for technical support. So we do have a really robust group of engineers and technical experts here at JM who are available to help you answer your questions. And you know, as we look at LNG systems, they're obviously very complicated. And so if you have any questions today, you can call this number and we will help you get your questions answered. We have people here who can help you revisit specifications for hot or cold temperatures. So if you're looking for additional support, this is a great number to take down, and that's 1-800-866-3234. And then finally, for everybody who joined us today, you will receive a certificate of completion, and this will be delivered to your inbox by Friday. These can be submitted by or for professional development hours, but it is important to remember that the governing body who assesses your professional development will determine whether or not they're accepting the certificate of completion. So with that, we're going to dive into some questions. Jim and Jack, are you guys both ready to go?
Yes, ma'am. I am.
Excellent. So the first question we have, Jim, is for you, and that is, when installing removable valve or flange covers on cryogenic insulation systems, 1, do you recommend a full vapor stop on both sides of the removable cover? And 2, what do you recommend using to fill the voids around the valves or flanges that have removable covers?
Well, The first part of the question is actually the easy one. Do you recommend a full vapor stop on both sides of the removable cover? Absolutely. Valves in general are weak points because the valve stems usually protrude from the insulation system. A removable cover would make it even more of a weak point. No removable cover is ever going to have a true vapor tight system like continuous vapor retarders on the rest of the system. So absolutely a vapor stop on either side, because the area under a removable cover is going to get water into it and ice is going to form. So you want to, and water is going to be present. So you want to protect the rest of the system from this weak area. It's easy for me to sit here and say avoid removable covers, but I recognize that they're sometimes necessary. So I would say you want to remove them you want to avoid them as much as possible. Where they are not avoidable, vapor stops, as I said, what you fill the spaces around or under them with is not that important. Other than in this particular case, do not use spray polyurethane, because they're going to be, since it's a removable cover, it's got to be there because the flange or whatever is being worked on frequently. So a loose fill glass fiber would be fine. It's going to get wet, but whatever you put in there is going to get wet. So I think that's not that. It's the selection of what you pack it with is not going to be all that important.
All right, thank you. The next question is, please explain the basics of calculations for insulation thickness tables.
This is a very complex question. It involves two different aspects. The first aspect is the inputs to your calculations. And there are a whole host of these. They include the pipe size, the reasons to insulate. Are you limiting heat gain, or are you limiting condensation control, or both? The orientation of the pipe, vertical pipes, flat surfaces for tanks and vessels versus horizontal pipe have different insulation requirements. The ambient environment, the temperature of the environment, the humidity, the wind speed, all of these are inputs into your calculations. And then also the jacket emittance and the temperature of the pipe will all be inputs to your calculations. Once you have these inputs, and as easy as it is to go through all those, it's sometimes difficult to select them. And you need to choose, particularly for condensation control, some pretty harsh inputs. But then the easier part to say, but the harder part to do, is that you use the calculation methodology that's taught in an ASTM standard, C as in cat 680. That is pretty much, to my knowledge, the only existing methodology out there in any kind of standard for calculating heat gain limits and condensation control, that is jacket temperature, for mechanical insulation. So the inputs that I described, coupled with the calculation methodology of ASTM C680 as put into some kind of software system, some kind of calculation tool, is what you use.
All right, thank you so much, Jim. The next question that we have is, what's the difference between PIR and PUF, and is one better than the other in an LNG application?
Well, PIR is short for polyisocyanurate, and PUF is short for polyurethane foam. And definitely PIR is better here. In general, I would say I have the greatest experience in North America and Europe, and you can't get polyurethane foam in large blocks there. Polyurethane foam would only be available in those geographies in a spray foam or in I guess pretty much only in a spray foam. And then in very high density. The very high density pipe support, like 10 to 20 pounds or 10 to 40 pounds per cubic foot, is also a polyurethane. The PIR is very similar to polyurethanes, but it has better flammability, that is lower better resistance to water, lower flammability, less. It has a better dimensional stability, so less movement than does polyurethane. The other and very important aspect is that PIR or polyisocyanurate, is always made in a very carefully computer-controlled factory. It's made in a continuous bun stock process and has, as I said, very, very good stringent quality control. Polyurethane foam, it can be made that way, but very often polyurethane foam is made in someone's backyard in a box. They'll buy an A and a B side, they'll mix them hopefully in the right proportions and pour them into a series of boxes. So it's called box pour. That can be done correctly and with high quality, but it very, very often is not. You'll get variation once you've mixed your A's and your B side together. You'll get variation from the first box you pour to the 20th box you pour just because the A and the B side have been mixed together longer with polyurethane box pours. So you'll get better consistency, better performance, and better quality from a PIR than you will from polyurethane. Next.
All right. Thank you, Jim. We do have a lot of questions coming in, so we'll keep going. What is the best insulation for cryogenics in LNG pipelines on the marine areas and only in tropical weather?
Well, you know, we're partial. We're biased. I'll admit it. I think PIR is the best. Cellular glass works very well also, but it is going to work. It's going to work really well also, but it's going to be higher in cost. We've got lots of experience with PIR globally. I would estimate probably 80% of the world's LNG pipe is insulated with PIR. You know, another 19% with cell glass and 1% cats and dogs, different things out there. So I don't think you can go wrong with PIR or cell glass. You're just going to get a lower cost, excellent performing system with the PIR. Go ahead.
Thanks, Jim. I'm going to bounce back really quickly to your insulation thickness tables. Somebody just asked why you didn't mention 3E+. Can you talk a little bit about why 3E+ won't work for cold application systems?
Certainly. 3E+ has several problems with it for cold. The first problem is that buried inside of 3E+ is a 3/4 degree F safety factor for condensation control calculations. Now you can work around this. You can't eliminate the 3/4 degree F safety factor, but when you get the table of results from 3E+, which lists the thickness required to achieve a certain jacket temperature, it will highlight the thickness that it thinks you need to use, but that thickness includes the 3/4 degree safety factor. You can, by eye, go in there and find the first thickness, that is the thinnest thickness at which the surface temperature exceeds the dew point, but that will not be the same as what 3E+ tells you to use because they include that 3/4 degree. 3/4 of a degree may not sound like much, but when you're talking about condensation control and the jacket temperature, it can make a big difference, particularly on very cold pipes like this. You could have a 2 to 3 inch thickness difference by including or not including that 3/4 degree safety factor. Someone might argue, well, a 3/4 degree safety factor is a good thing to include. Well, we're the insulation manufacturer. We sell insulation, and we don't think it's a good thing to include, even though including it would cause us to sell more insulation. The reason for that is we already have safety factors built into other aspects of the design. We have a safety factor in our thermal conductivity values that are used. We have a safety factor in that we are already selecting very harsh climatic conditions. You don't need to put in a third safety factor, especially one that's hidden in the guts of the program. The second problem with 3E+ is that it does not handle insulations that have blowing agents in them correctly. 3E+, you have to understand, was written by an organization called NAMA, which represents, Johns Manville amongst them, the glass fiber manufacturers. Excuse me, not glass fiber, but mineral fiber. And they deal almost exclusively with hot applications. And they don't have blowing agents. So it did not occur to them to modify the program or to write the program to handle thermal conductivity curves that are more complex. So I'm getting into the really deep bowels of 3E+, but in general, do not use 3E+ for cold calculations. Instead, call JM, call Owens Corning if you're going to use cell glass, call whoever is your closed cell cold insulation provider. They're going to have their own computer programs that are written based on C680, just like 3E Plus is based on C680, but do not have the flaws that 3E Plus has for cold. Now, don't get me wrong, 3E Plus works perfectly for hot applications, but it has its problems with cold. We've brought these to the attention of the owners of 3E Plus, and we're hoping that they will fix this in the future, but right now, I recommend not using it for cold applications.
All right, thank you, Jim. So we've had a couple questions come through asking about the comparison of silica aerogel for cryogenic applications to Trimer, and I think it specifically is referencing this slide here. Can you talk through this slide once more? One of the questions was specifically not really understanding how the thickness translated to layers. So just one more talk through that for me, please.
Sure, no problem. Silica aerogel has a thermal conductivity that's roughly half, remember lower is better, roughly half that of Trimer PIR, which will result in a thickness requirement of roughly half. You can see the thickness here of 7.5 versus 4.5 for Trimer PIR and aerogel. The aerogel is a little more than half here, but it's in the ballpark of half. So the total thickness of aerogel is going to be roughly half that of PIR. PIR can be installed in each layer at up to 3 inches of thickness, whereas aerogel can only be installed at 10 millimeters of thickness per layer, a little bit less than half an inch. So even though the silica aerogel in this particular example of 4.5 inches of thickness is less total thickness than PIR, it's 12 total layers because each layer of aerogel is 10 millimeters or a little less than half an inch of thickness. This is a limit of the aerogel products. They only come in a maximum of 10 millimeters thickness. I don't understand the full manufacturing process, but for whatever reason, the aerogel only comes in a thickness of 10 millimeters, so you need a lot more layers to install the aerogel, and each layer has to be individually installed. It's not like they're all glued together into one installed device made up of multiple layers. You install each layer individually. So where you would install 3 layers of PIR, you'd have to individually install 3 layers of aerogel, even though the total thickness is 4.5 inches compared to Trimer's 7.5 in this case. I hope that answers the question.
I believe it did. All right, the next question is, I'm interested in anything that you can do to minimize CUI, particularly on a carbon steel pipe. Do you coat the stainless, or are you coating stainless steel pipe prior to insulating, and if so, with what? Given that most LNG plants are located near the coast, often right on the seawater, how does the location factor into your CUI mitigation efforts?
Okay, the first thing to realize is that carbon steel pipes can only be used down to a certain temperature. I'm sure that the metallurgists know why, I do not, but carbon steel pipe is used only down to maybe minus 40, minus 50 degrees F. Below that, carbon steel will embrittle. So in LNG applications, you would never use carbon steel pipes. So let's wipe out from our minds corrosion of carbon steel pipes for LNG applications and deal with only the corrosion, the CUI potential for stainless steel, which is what would be used in LNG. Stainless steel's corrosion is typically called stress corrosion cracking, or SCC. And the stress corrosion cracking of the stainless steels that are used in LNG pipes is something that has to be thought about. Fortunately, stress corrosion cracking, like all types of corrosion, is a temperature-related phenomenon. Stress corrosion cracking of austenitic stainless steel will only occur within a temperature range of about 140 F up to around 250 F, somewhere in that ballpark. Below that temperature range, that is below 140 F, the chemical reaction of stress corrosion cracking of the stainless steel is slowed to insignificance. And above that temperature, above 250, maybe a little higher than that, but above that temperature range, you cannot get water to the pipe surface. the pipe is too hot. The water will boil off before it reaches the pipe. And water is necessary for stress corrosion cracking to occur. So in LNG pipe, you're typically not going to be in the 140 to 300 degree or 250 degree temperature range. Even if you had LNG pipe, which was used periodically. LNG flowed through it like a loading line, and then it was emptied and allowed to rise to room temperature. You're not going to get up to 140 degrees. So the corrosion under insulation for stainless steel pipe should not be an issue in the LNG environment because you don't operate below 140 degrees F. If you did have carbon steel, I mean, this is getting a little off topic, but if you did have carbon steel pipe, which also has a temperature range, but it's about 32 degrees F, 0C, up to around 250 F, there you do have to be more concerned about CUI, because even if the pipe was cold, below the 32, if it was operated only periodically, it might get up to room temperature where corrosion could occur. The best way to prevent corrosion is a multi-pronged approach to keeping the corrosive parts of the equation from all occurring. And the most important of these is to keep water out. Water is a requirement for both types of corrosion, stress corrosion cracking of stainless steel as well as normal oxidative rusting of carbon steel. People will often worry about the chloride content of the insulation materials, and PIR does have some chloride ions in it. Somewhere in the 50 to 90 parts per million of chloride ion after certain testing can be detected. I won't get into the details of why that level of chloride ion is not really present in a cold application, but in certain tests it will show that level of chloride ion. But in order for that to cause any problem, water has to get into the system. And if water's getting into the system, it's coming from the environment and can bring with it a virtually inexhaustible supply of chloride ion. So the real key is to keep water out through a multi-pronged approach. Proper jacketing to shed liquid water, the proper vapor retarders to keep water and water vapor out, a closed cell insulation like the trimer, and the proper joint sealing to also keep water out of the system. So this very complex multi-pronged approach to keeping water out is the right way to go about preventing CUI. If you still expect there to be some water getting into the system, and if you're in the right temperature range, as I said, this would not be true of LNG pipe or stainless pipe in general for LNG applications, but for carbon steel, it is also possible to coat your pipes, either with some type of multi-part epoxy coating, or there are reactive gels that are used very frequently on carbon steel pipe today. That's what I have there, Kim.
All right, thank you, Jim. The next question we have is, I'd like to know more about joint staggering between two fittings, as this will help me do the piping design so that I can later avoid costly modifications.
Well, we showed joint staggering in our pictures. Joint staggering depends upon the number of layers, but in general, you want to stagger your longitudinal joints, which I don't think would really pertain to the question here, but you want to stagger your longitudinal joints about 90 degrees of circumference from each other. If you're talking about joint staggering between two flanges or 2 points in the piping system, they're more likely talking about staggering of the butt joints. In general, in an LNG system, you're going to be staggering your joints by a minimum of 3 inches and up to roughly half the length of a section of PIR insulation or cell glass insulation, and that length would be that staggering, or the piece length for PIR is 3 feet or 36 inches. For cell glass, it would be 24 inches. So you would stagger roughly up to a maximum of about 18 inches for PIR and 12 inches for cell glass. I'm not quite sure how this relates to a fabricator cutting parts more efficiently, but maybe if they were to, in a given run, cut a piece to 18 inches. That could be used, or cut one layer to 18 inches and the other layer left at 3 feet. That could be achieve the correct amount of stagger. But anywhere between the 3 inches and the 18 inches of butt joint staggering between layers is what would be recommended. I could easily be misinterpreting this question. If whoever asked it wants to get in touch with JM and explain it in more detail, I bet we can help out, but I'm not quite positive how what I just said would relate to them being more efficient in their fabrication.
All right, thank you, Jim. And per your answer to that question, I'm just going to leave this up here for anybody who wants to get in touch with JM after this presentation. You can contact us at that phone number. The next question for you, Jim, is we have water dropping from outside insulation of LNG insulated lines due to condensation. The lines couldn't be isolated as it's continuous running plant. How can we tackle such a situation?
The word isolated there, I'm not sure what it means. Could have been a typo or something. They probably mean that they cannot shut the system down and tear off the insulation and put new on. That would be my guess as to their limitation. Condensation of an insulation system usually means that someone misidentified the harshness of the climatic conditions. Most likely, they either have less wind or higher relative humidity than they designed for. I want to contrast that with ice formation. If you get ice formation on your jacketing, that is an indication that your vapor retarder system has failed and you are getting tremendously cold temperatures on the jacket surface, which means your insulation is not working worth a darn. Condensation is not a terrible situation. Ice formation is. So the good news is that if you're getting some condensation, it's not the end of the world. Your insulation system might be working just fine, and you're only going to get condensation on those periods of the day or periods of the year when you have particularly high humidity or particularly low wind. So my first advice would be to see how often this condensation is occurring. Is it periodic? Is it for a little while each morning when the dew is falling or forming rather? If so, maybe you ignore the whole problem. If on the other hand it's happening all the time and you decide that more insulation is necessary, it would certainly be possible, assuming that the insulation system is still functioning properly and that this is just a design issue, it would be quite possible to remove the metal jacketing, put another layer of insulation on top of the existing insulation and vapor retarder. You would need to put another vapor retarder on top of this new section of insulation, and you would need to install new metal jacketing because the old jacketing will no longer fit. It was designed for whatever the original circumference was. So this is a repairable situation, but I would urge caution before taking the time and expense to repair it, to make sure that that repair is necessary by observing how frequently the condensation is occurring.
Great, thank you, Jim.
No problem.
The next question I have is, can or should cryogenic insulation be glued to the process piping when it's down at ambient temperature? This would allow adhesion to complex shapes.
I think the answer is no. I'm not sure what they mean by down. So I'm going to treat this as a slightly different question. Should the insulation be glued to the pipe when it's first installed? Well, you know, when it's being installed, the pipe is down at, well, up at, if it's LNG pipe, it's up at room temperature, and that would be the time you would glue it on if you were going to glue it. But I think the answer is no. You do not want to glue your innermost layer of insulation to the pipe. You want that insulation to be free to float on the pipe to accommodate expansion and contraction. Complex shapes typically aren't going to occur on pipe, even on elbows. I would not consider those complex. Excuse me. If you did have a complex shape like a valve or something, those are best handled by either buying prefabricated insulation to fit tightly against the valve or making boxes with insulation and then filling the voids with loose fill glass fiber and maintaining your vapor retarder along the surface, on the outer surface of the insulation. But even in those kinds of complex situations, I don't think you want to glue the insulation to the pipe. There do exist warmer situations where you have where you have vessels, and sometimes in vessels, it's necessary in the installation process to glue the insulation to the vessel. But this is more of an installation issue. If you could somehow magically, once the system was installed and the jacketing is in place, if you could magically reach in and remove the adhesive that's holding the insulation to the tank, you could do so. The insulation would then be held by the jacketing in place, will be held in place by the jacketing. So that adhesive is only done on a small part of each individual piece of insulation to hold it in place. I've not seen this done on LNG pipe, nor do I think it would be a good idea.
Excellent. Thank you, Jim. The next question is there any online insulation damage repair technique in LNG pipelines that you can do without shutting the system down?
This kind of gets at the inspection and maintenance aspect that Jack talked about. If you find small areas of damage, if you find some jacketing that has opened up, that is slid, where metal pieces have slid, that can be repaired. If you find a hole in your primary vapor retarder where some metal jacketing has slid open and a bird has pecked at it, that can probably be repaired without shutting the system down. If you've got damage to the point where ice is forming, then the answer is no. Your entire insulation system is compromised and really needs to be replaced, which cannot be done, cannot be even done from a safety point of view on an LNG pipe operating at minus 165, let alone from the point of view that ice is going to be forming on it faster than you could scrape it off to put the insulation on. So I think the answer depends on how much damage and the type of damage that you're seeing. If it's corrosion of the jacketing, and if the vapor retarder underneath it is intact, you could replace the jacketing. If it's a sprung piece of Band-Aid, yes, that could absolutely be replaced. But if your vapor retarder and insulation system have failed to the point where your system's got lots of water and ice in it, then no, I do not think it can be repaired without shutting the system down, or at least that portion of the system. This is also related to vapor stops. We talked about the cost-performance continuum. One of those costly aspects is the frequency of vapor stops. The more often you put in a vapor stop, the more you're going to have to pay, because vapor stops are not free. They cost money, they cost labor to be installed. But the more frequently you put them, any damage that would occur is going to be isolated to the area between the vapor stops, which would make that less of a concern. If you had a vapor stop every 20 feet, then the portion of your insulation system which is no longer functioning is only 20 feet. Perhaps, now you'd have to do some engineering here, but perhaps the amount of heat gain through that 20-foot section into the LNG would not be a catastrophe, and you could just ignore the problem. On the other hand, if your vapor stops are every 100 feet, well, that's a lot of heat gained into the LNG, a lot more boil-off gas, a lot more risk of pressure building up, etc. So part of this is there are interrelationships between the cost-performance decisions, such as frequency of vapor stops, and the inspection, maintenance, and repair work that might be needed in the future. Next.
All right. Well, speaking of vapor stops, that's the next question, is can you go through how to install vapor stops and contraction joints in detail? Or should we save that for an offline question? That might be pretty detailed.
Yeah, why don't you let me contact that person individually? It's so hard to describe these things verbally when pictures and drawings are so helpful. The key for a vapor stop is continuity of a vapor retarder from pipe to primary vapor retarder. You're stopping the movement of water and water vapor down the length of the insulation system. That's really the key. But as far as the details of them, I think that's best left to discussion. You can find some examples in our trimer in cryogenic or LNG applications installation guide. You can get more information there on our website. But I'll talk to that, or I'll begin communicating with that question asker directly.
All right, excellent. The next question is, the presenter equivocated the need to put caulking on the jacket and said it could limit evaporation out. Then said if the caulking is installed, it should be installed on the inside of the jacket joints, not as a bead on the outside. This next part is a quote. How the heck do you do that?
I'll take this one. You have to caulk on the inside of the jacketing before you put it on the pipe, so that when you put it on the pipe and close it, you've now smashed the sealant against the laps from the prior piece of metal on the circumferential joint and against itself on the longitudinal joint. And the reason you want it on the inside is because it's caulk. And we've all caulked around our windows, and we've been using caulk for years, and clearly any caulk is going to last a lot longer if it's not exposed to sunlight or weather or things like that. But it's a complicated process if you're going to caulk the metal joints. You've got to put the caulk on first and then the piece of jacketing on.
Excellent. Thank you, Jack. So, Jim, the next question for you is, in your three-layer insulation image, you had the longitudinal seam on top. Is this what you recommend?
Well, I could have screwed something up. I thought in my three-layer drawing, I had the outer layer longitudinal joints at the 3 and 6 o'clock position. If I did not, my apology, and I screwed up the picture.
No, the picture, hey, Jim, the picture was right. On the three-layer, I believe it was 3 o'clock and 9 o'clock.
Okay. Then let's assume it was right, and I'll just describe what our recommendation is. The outer layer should have its longitudinal joints at approximately the 3 o'clock and 9 o'clock positions, because the forces that get exerted on the pipe from something hanging from it sitting on a support, from people walking on it, and we of course know that never happens, are generally exerted at the noon or 6 o'clock positions, and you don't want those forces to be exerted directly on the joint if you can avoid it. So we want the outermost layer of insulation's longitudinal joints at 3 and 9 o'clock, and then roughly 90-degree staggers from there. So the second layer in a three-layer system would have its joints at the noon and 6 o'clock position, continuing on for et cetera.
All right, thank you. The next question is, where do you recommend using dovetail joints?
Dovetail. I recently saw a patent about dovetail joints being used, but I've never actually seen a dovetail joint used in practice. A dovetail joint is a joint that spreads out and would be extremely difficult to install. So let's assume for a moment that they're talking about shiplap, tongue and groove, or spline joints rather than dovetail. This is all a cost-performance continuum issue. Every one of those joint treatments is going to cost more money to fabricate and more money to install. They're going to give you a little bit better performance, though. So where does the specifier and facility owner want to operate in that cost-performance continuum? In my experience, the vast majority of joints, LNG included, are flat joints, and if you apply the joint sealant properly on a flat joint, you can achieve the necessary performance. And to reiterate what we said during the presentation, the proper way to install joint sealant on a flat joint is as a thin, even layer across the entire joint face. It's thin to avoid a thermal short because joint sealants are not good insulators. So you want to have as thin a layer as possible to minimize heat transfer through that joint. And you put it across the entire layer, or excuse me, the entire thickness of the joint, the entire width of the joint, to maximize your adhesion. So I don't really think that with proper design that shiplap, spline, and tongue and groove are necessary, even though they were in some of the pictures that I provided. One possible, I won't say exception, but one place that I've seen them used reasonably frequently is at pipe supports. I'll see a pipe support designed with a shiplap joint to butt up against the neighboring pipe insulation. But if that occurs, you have to be very careful to assure that the shiplap's thicknesses are of the pipe support exactly match those of the pipe insulation, because they're going to be fabricated by completely different companies, completely different people who might have slightly different tolerances in their tools. And so you may not get a perfect match there. So you do have to watch out for that. Next,
All right.
Kim.
The next question is, I'd like to know if expansion and contraction rates for cellular glass and PIR affect the quality of the insulation system.
Cellular glass has a better, that is lower, coefficient of linear thermal expansion, COLTE, I abbreviate it. Cellular glass is lower, closer to that of the stainless steel than is PIR. So that helps. You need fewer expansion-contraction joints in the cellular glass, but in my experience, you still need some. You just need fewer of them. A properly installed PIR system can still, even though it has a higher COLTE, can still be designed and installed and will work for the 20 or 30 plus year lifespan. You just have to properly engineer it and put in more expansion contraction joints. But these are a well understood part of the insulation system, and spacing and design of them are well understood and can be readily calculated. Also remember that in general, there are probably engineers that do it differently, but our recommendation is that expansion contraction joints are not needed on the innermost layer, because the innermost layer's joints are not sealed, so virtually every joint can act as a small expansion contraction joint. Go ahead.
Right.
Kim.
The next question is also related to cellular glass versus PIR, and it says the only benefit of using cellular glass over PIR flammability, or are there other advantages to cellular glass over PIR?
Well, certainly cellular glass has lower flammability, but remember, you're in an LNG or a chemical processing plant. Flammability is, while it's important, the insulation contribution to that is of very minor importance. The exception is there may exist specific small areas of a facility where you design for a pool fire to occur. And maybe in the event of an LNG spill, you design it to collect in a certain place and have a pool fire. And if it was unavoidably necessary to run pipe insulation or a pipe with pipe insulation above that pool fire, you might need a highly fire-resistant insulation system, which would be stainless steel jacketing, not aluminum, and cellular glass insulation. But these are small areas for pipe insulation. So flammability is a benefit of cellular glass, but I don't think it's a significantly important one in an LNG application. The other benefit of cellular glass is it does have it has better water resistance, lower water absorption, lower water vapor transmission. However, again, we go back to the nothing succeeds like success idea, and PIR with a proper installation, and PIR is closed cell as well, not as water resistant as cell glass, but still water resistant. But with a proper system design, the proper vapor retarders, the PIR system can be made to work and last, the lifespan expected.
All right, thank you, Jim. The next question is, the webinar has been for LNG at minus 265 degrees Fahrenheit. Is Trimer also good for liquid nitrogen service? I believe that temperature is minus 325 degrees Fahrenheit.
Short answer is yes, but I'm rather long-winded, so I'll give you the long answer version. You will see on our data sheets that we quote a lower temperature limit for trimer PIR of minus 297 degrees F, which happens to be the boiling point of oxygen. Liquid nitrogen, as the question asked, is around minus 320 F. So there's nothing magical that happens to PIR that it loses its insulating ability or it turns to dust or something bad happens to PIR below minus 297. We quote that as the lower temperature limit so that we have the opportunity to caution anybody designing any insulation system or designing an insulation using any insulation of the dangers of a system operating below minus 297, which in general is going to be liquid nitrogen, liquid hydrogen, or liquid helium. There might be some more exotic gases, but mostly it's those three. And of those, liquid nitrogen is far and away the most common at minus 320. So designing those systems it's very important to keep out not only water, but to keep air out of your insulation system, because air reaching the pipe surface at minus 320 has the potential to condense oxygen out of the air, and there's not a whole lot of things around that are more dangerous than liquid oxygen for both corrosion as well as flammability concerns. So we use the minus 297 limit as a caution, or as an opportunity to caution people to make sure that they have extremely high quality vapor retarder systems designed with air as well as a water intrusion in mind. But nothing inherent in PIR prevents it being used below minus 297. In fact, as with all materials, it continues to get better in insulating ability as you go colder.
All right, thank you, Jim. The next question is it recommended to use HDPE over PIR for more insulation efficiency?
No, short answer, no. HDPE, high-density polyethylene, is a type of jacketing. If you were to select HDPE as a way to get better insulating ability, you'd be far better off just using another inch of trimer. Your cost of HDPE as an insulator is going to be huge compared to getting the equivalent insulating ability from a tiny bit more trimer. So I don't think you would ever use HDPE as a way to get insulation ability. HDPE might be selected for an emittance point of view, although it's going to have an emittance of 0.9. The range for emittance is 0 to 1. Aluminum is going to be 0.1, stainless at 0.3. So you get a significant jump in the emittance of PE at 0.9, but painted aluminum would be a 0.8. So you're going to be almost the same as using HDPE. I've seen HDPE primarily used not as a separately applied jacketing in the field, but rather as a pre-insulated pipe jacketing. So I've seen it applied in a shop or in a fab facility on site where people are using what's called pre-insulated pipe, where you start with a pipe and then you apply in the fab shop or in a factory an insulation, usually polyurethane, and then possibly a vapor retarder, and then an HDPE thick jacketing. So it might be used for that purpose, but I don't think it would be economically viable or a good idea at all to use it to replace a certain amount of trimer because it's going to have, while it's certainly better than metal at insulating, HDPE is not a very good insulator.
All right, we have 1 minute left, so we're going to ask one final question before we wrap up here. And this question is, I'm curious why there are double vapor barriers required between the second and third, or at the second layer and at the third layer.
I think this is a cost-performance continuum issue coupled with the longevity desired for the LNG facilities. And then lastly, the mission criticalness of the insulation system. You know, if you're making sausage and you've got some refrigerant running at minus 40 or something in a food plant, you know, your insulation is primarily designed to save you some money. every bit of heat that enters into your refrigerant is just that much harder your compressor has to work to cool the refrigerant. So it's a cost factor. In an LNG plant, while there's certainly a cost issue, there can be refrigeration, you can have boil-off gas, etc. There's a danger associated with heat gain into LNG, which is not present in a refrigerant or in other cold applications. I mean, the amount of energy embodied in a loading or unloading facility and the amount of LNG stored there probably borders on an atomic bomb. So, okay, that's specious because it's not going to all explode at once. But you get the point that there's a lot of energy involved in an LNG plant, and the insulation system is extremely mission critical. So the double layer vapor retarder, or excuse me, the double vapor retarder is just belts and suspenders as part of a high performance, higher cost point of operation on the cost performance continuum. That's
excellent.
probably where we got to wrap it up.
So much. We do have to wrap it up. We will get all of these questions answered. If we did not answer your question in the webinar today, we will send you a message privately, reaching out to you with the answer to your question. And we thank everybody for your time today. Just another reminder, your certificate of completion will be in your inbox by Friday. And we thank you for your time. Stay safe, stay healthy, and we will hopefully hear from you soon.